So good morning everybody, and welcome to this morning session. So our first speaker this morning is Professor Zagier from the Max Planck Institute in Bonn and Collège de France, still in France. So it's a great pleasure to have you here, please.
Okay, thank you. So, and thank you for the organizing, for the usual. It's wonderful to be here. So today I think there are several talks related to quantum invariance of knots. We already had one yesterday, at least one. So I won't try to review everything. But my story is really about, well, first maybe I should give, did you give my title?
I'm sorry, I didn't.
I think you didn't, but I can give it.
Your title is Kashaev invariants, Nahm sums, and modularity.
Yeah, so I want to read it in somehow. So Kashaev invariants, Nahm sums, and modularity, because I want to somehow introduce them a little bit at the beginning so that I don't forget in particular and not get around to the Nahm sums at all. So this is an invariant of a knot. You have a knot and an integer n, and there's an invariant, that k is not for Kashaev, it's for knot. Then there's a Nahm sum. This n is not for Nahm, it's for n. So the Nahm sum is something, well, I can already write it down. In the simplest case, it's the sum q to a quadratic form, which for some perfectly good reason I won't explain, you write like this: q to a quadratic form divided by qn, and qn is the famous Pochhammer symbol, 1 minus q times 1 minus q squared, to 1 minus q to the n. So you have this Pochhammer symbol, and modularity, I remind you about it, of course we've all seen it before, and it came up in many talks before. It came up in Heidegger's talk in particular yesterday, maybe others. The modular form is roughly something that transforms like that under SL2Z or some similar kind of a group. So this I'll explain in a minute. There's something. And the last ingredient is number theory. Well, you can say modularity is number theory, but specifically algebraic number theory, which means numbers that aren't just rational numbers, but numbers that belong to Q bar, or to maybe a fixed number field, which means the field of finite dimension over Q sitting in Q bar. So, and the point is really that the connections with algebraic number theory are very, very deep. It's not just that occasionally you get a number that's, you take a square root of 3 or something, but really very, very non-trivial algebraic number theory. So just to start the ball rolling, so K is always going to denote a knot, and usually, well, not always, it's going to be hyperbolic knot for everything that I say. So, I mean, everything will certainly also be true for simpler knots, like torus knots, but none of our examples are for that, and they're less interesting, and there'll be many slightly exceptional statements. So if you have a hyperbolic knot, then you would associate a 3-manifold, the knot complement, but by rigidity it has a unique hyperbolic structure. It's got a unique metric with constant curvature 1, minus 1 perhaps, to make it better. And uniqueness, it's uniquely unique, well, it's not quite uniquely unique. Up to conjugation, it can be written as hyperbolic 3-space divided by gamma, where gamma is in the automorphisms of hyperbolic 3-space, the isometries, which is SL2C, SL2C, I guess. Oh, sorry, gamma is contained in a group which, up to renaming things, you can assume it's a nice group in that. And now this group is unique up to conjugacy. And so if you take the set of traces of the elements where gamma runs over that whole group, then each of those is, of course, an algebraic number, again by rigidity. It follows that the entries of each gamma can be chosen after conjugation to be algebraic numbers, so the traces are algebraic numbers. So this is in Q bar, but and they don't depend now on conjugation, so they're uniquely defined, but of course you don't know which gamma to take, so you have to take them all, or a set of generators. If you take the field generated by that, this is called the trace field. I'll try not to write below the line, but just as vocabulary. Trace field of the knot, and that's an invariant, and that's already a non-trivial piece of algebraic number theory, because this is some non-trivial number field. So that will play a role. So I just want to introduce the main characters and the main notations. The other main character notation is Stavros Kavafalidis. So essentially all of this, everything I have to report, well, one or two things I found by myself, but essentially it's all joint work with him. And so I'll often write who did what, and since his name is very long, VAR means Stavros. On the other hand, if I have to write, for instance, the name Le, I will not abbreviate it, because it's not really essential. Okay, so those are the notations. So let me start now with the z is e to the 2 pi I z, and if n is a natural number, then zeta n is the standard nth root of unity. Primitive nth root of unity, just e to the 2 pi I over n. So I don't have to keep writing those things. So the Kashaev invariant is a well-defined, it's a knot invariant that takes values for every n in the field, in this field. So already we have some rather non-trivial number theory, because we have a variable field. So if you take the totality of all these invariants, they're taking values actually in Q abelian, the maximum abelian extension of Q. And the famous volume conjecture, Kashaev's volume conjecture, and there's also the AJ conjecture, both of which were mentioned and explained yesterday. The volume conjecture tells you that if you take Kn for n very large, then it grows exponentially in n as a constant. I'll just put c times n plus little o of n, where the constant is 1 over 2 pi times the volume of the same n that's written here as 3 minus k. That's a well-defined hyperbolic volume. So I'll come back to this in a moment, but as I say, I want to start by having the three ingredients each separately around. So a Nahm sum is a Q hypergeometric series. So such a thing is called a Q hypergeometric series. Such a thing meaning a sum of this form. It could also be multidimensional, it will be in a second. So Q hypergeometric means it's a sum of some term. The term for n equals 0 is just 1, and the ratio of the nth term to the n minus first term is just a rational function of q and q to the n. So you see that if I take this term, call this Tn for the nth term, then if you take Tn divided by Tn minus 1 in this particular case, you'll get q to the an plus b minus a over 2 divided by 1 minus q to the n. And you see that now there's no longer a product, this is just a rational function of two variables, q and q to the n, but that rational function is independent of n. So if you, of course, you can say a rational function of q to the n is also a rational function of q, but you think of q to the n as an independent variable, and that's called q hypergeometric. So the Kashaev invariant is also given by a q hypergeometric series, but some q hypergeometric series terminate. So let's say I took this hypergeometric series, which actually I studied once alone and with Kashaev and found interesting connections also to knots with Kashaev invariants. If you take this thing, it doesn't converge as a power series. This thing is convergent as a power series in Q, and also numerically if Q is less than 1. But if you take this thing, it doesn't converge as a formal power series at all, because each term begins with 1. And there are infinitely many, so it obviously doesn't converge. It doesn't converge numerically for any Q at all. But if Q is a root of unity, so if Q is in the mu infinity, the set of numbers, some power of which is 1, then of course it simply terminates, and then it does make sense. And the Kashaev invariant is given by such a terminating hypergeometric series, which is why it then takes on values in that cyclotomic field. So we already have, although they come from different parts of mathematics, and I haven't yet said why the Nahm sums arise at all, but in mathematics, but they both are Q hypergeometric series. And the more general Nahm sum, I should say, would be multidimensional. For instance, you could have an n1 and an n2, and then this would become a quadratic form in n1 and n2, a linear expression and a constant, and this would be the product of the Pochhammer symbols qn1 and qn2. So that would be a non-terminating two-dimensional hypergeometric sum. So that at least makes some sort of a vague connection here at the moment. These are both chaotic geometric sums. Now let me say the connection between Nahm sums and modularity. And for that I should say something briefly about K-theory. So another ingredient, I don't want to go into the block group in K-theory at all, but if you have a number field, or a thing called the block group, which is known to be isomorphic essentially up to tensor root 2, let's say, to keep things simple, to the third K3 of F, this is algebraic K-theory. This is a thing that's difficult to define and essentially not computable at all. Here you can compute, and the block group, I don't want to go into details, but a typical element of the block group is a certain sum, the formal sum, so like a divisor, of elements of the field with integer coefficients, which satisfy an auxiliary condition. I'll just write it down for completeness, but I don't want to go into this. So there's a condition, and then it's such sums modulo, so it satisfies this relation, and then modulo a certain relation, which is the 5-term relation, which at the level, say, of the dilogarithm function, so the dilogarithm function associates to every number, every complex number z, this is the Bloch-Wiener dilogarithm, a real number, and it's a function that's one level higher than the usual logarithm, and it satisfies a 5-term relation. You divide by the same 5-term relation, so that here you have a map to R by just sending this thing to the sum ni d of zi. So the block group is well, we know now it's a finite rank group because of this theorem, and Borel's theorem that tells you that the rank of this is finite and known. So it's a sort of a controllable group. In all of our cases, we'll have ranked 1. And then you have a way to evaluate using the dilogarithm function. I won't write down the exact function, but the specific elementary function discovered essentially by Euler that gives you a number. And now the connection with this story is that in the Kashaev invariant, we have the Kashaev's volume conjecture that the asymptotics are given the leading order by this constant, and the constant is the volume. But since you can triangulate this number, the volume of n, if I triangulate delta into some simplices, you can always triangulate this knot complement. It's a non-compact manifold at the end. You can triangulate with ideal tetrahedron. So the 4 corner points of the tetrahedron are all in infinity, and the infinity, the boundary of hyperbolic 3 space, is a Riemann sphere, S2, and it's up to PSL2C, so 4 points have a unique invariant. That's the cross ratio. So xi is the cross ratio of the vertices. And then the connection of this with the dilogarithm and then the block group that I just mentioned is that the volume of the tetrahedron, the ideal tetrahedron with 4 corner points whose cross ratio is xi, is exactly this dilogarithm function of xi, and therefore the volume of n is simply the sum of the d of xi, but that's exactly d of xi. So it turns out that if you associate to n xi n, which is the sum of these xi's, the formal sum, over whatever they are. So you take any triangulation into ideal tetrahedron, xi the cross ratio of the vertices, you have to do something with normalization, orientation, and you take the sum of the xi's, then it will automatically satisfy this relation here that follows either from an old paper of Neumann and myself, where we write down some consequence of the gluing compatibility at edges. It also follows from the work of Dupont and Salle on scissors congruences. So you get a canonical invariant. Well, it's not in this block group, and it's canonical because you can go from any triangulation to any other by special moves, especially the 2-3 Pachner move, and 2 plus 3 is 5, that corresponds to this 5-term relation. So believe me, there is a well-defined map that associates to a manifold an element in the block group of Q bar, and I didn't say what F is, but F in our case will be this trace field. And so that's already very non-trivial number theory, because the block group, or algebraic K theory of a number field, is a very, very deep algebraic number theoretical invariant. So we already have many connections between the ingredients. You have the block group, which will come in a second in relation to the Nahm sum. So Kashaev invariants have to do with nuls, and therefore 3 manifolds. And so the last ingredient that I didn't put in my title, but that will connect in a minute with Nahm sums, is the block group or algebraic K theory. Block group. So
What this square bracket xi means?
it's just a symbol, it's a divisor. It's a formal combination. So for instance, let's say it's Q, then an element of the block group would be 3 times 2 minus 7/3. But I don't want to multiply 3 times 2 and subtract 7/3. I mean, it's just a symbol, it's a divisor. So it's an element of Z of F, and then xi wedge 1 minus xi 0, for instance, this would be 2 wedge minus 1, and up the torsion it's already 0, because minus 1 is 2 torsion. But here I get 7/3 wedge 4/3, or minus 4/3 maybe, and then I would have to multiply it out. This is the multiplicative group, so this would be 7 wedge minus 1 is torsion, 2 is 4 is 2 squared, so this would be 2 times 7 times 4 minus 7 times 3, and so on. So you multiply things out in terms of primes, and the whole sum has to sum to 0. But I don't really want to go into that. I just want to say that there is this block group, which is a very deep invariant, and just, well, some final number theory, you know that if you have a number field, its degree is finite. Of course, it's traditionally written as R1 plus 2 R2, where if you take a defining polynomial of the field, it has R1 real roots and R2 pairs of non-real complex roots, and then it's known by Borel that the rank of the K theory, and then the theorem of maybe Sust and Merkurjev, that Levine shows that these groups are equal. That tells us that the rank with the dimension over Q in your tensor of Q is equal to R2. So we know exactly what it is. So this is, those are the main ingredients. Now before I come back to knots, which is really what I want to talk about, the Kashaev invariants are the main thing I want to talk about, let me say a little more now about Nahm sums and why why one would even think that they might be connected to this whole topological story.
Excuse me, is it easy to determine fk for given hyperbolic number?
Yeah, if you have a triangulation, it's easy. So let me give, actually that's a convenient question, because I can use it to draw 2 pictures, which I'm very, very bad at drawing pictures, but I'll try.
What?
So let me draw them. The 2 knots that I'll take is my standard ones to discuss. This is really, I never know how people, some people can just do this in real time. And it just comes out right. Okay, this one is called 4-1 or figure 8 knot. And then there's one that's even harder to do. No idea what this is. It's more or less, anyway, it doesn't matter. The picture can be found on Google anywhere. So the two of the very simplest hyperbolic knots are these 2. And here, the field F is simply Q of squared minus 3. So this is the simplest quadratic field. It's got the smallest discriminant of all quadratic fields. In absolute value discriminant, well, discriminant is absolute value is 3. And this field here is Q of alpha, where alpha cubed minus alpha squared, I think minus 1, it might be alpha squared, the isomorphic fields, it's correct, minus alpha squared, but it's plus 1 is 0. So, of course, then there are 3 roots, and I have to say which one, because they, so I take the, well, it doesn't matter, but I have to take one of the non-constant. I mean, the abstract field is just the abstract field, but the actual field we want has to be embedded in C in order that I can do this dilogism. So you have to pick, and the particular, so it's actually, these are not abstract number fields, they're subfields, not of Q bar, but of C. It's been embedded into C once and for all. Otherwise, you can't evaluate the dialogism. So to repeat what I've said so far, given a knot, you get a manifold. Given a manifold, you have a class psi m, which is the sum of the xi's being the cross ratio of the ideal tetrahedron of the triangulation, which is in the block group now of the corresponding field. Okay, and it's well defined. It doesn't, the sum depends on the choice, but up to the 5-term relation, it's well defined. Okay, now I want to come back briefly to the Nahm sums. So Nahm had the following, if you look at the classical literature, if you see Gauss and Euler, then you see that the Nahm sum, as written there, is a modular function. So a modular function, actually I don't need this thing because mine will actually only be modular functions. So simply invariant under the Galois group. It turns out that the Nahm sum is a modular function in several classical cases. For instance, if A, well there are 7 values and I don't have them written down. I know the A's, it's 2, 1, or half. And then the B, I forgot to write down the table. Maybe it's 0 and 1, -1, 0 and 1, and 0 and minus a half, or something like that. I'm sorry, I don't have to put it down, and it doesn't matter. I'll just write down some numbers, 1/48 and so on. So this Nahm sum, which depends on 3 parameters, the classical literature, well, I'm not sure if all 7 identities are known, but there are 7 cases where one happens to know by various classical identities, or it's easy to prove, that you get a modular function. So this is absolutely amazing. If you write down the worlds of modular functions, I didn't say the relation, of course, Q as usual is e to the 2 pi z. So any modular function in particular is translation invariant, so it has an expansion in Q. It has a power series expansion in Q. And any hypergeometric function like this has a power series expansion in Q. But there's utterly no reason that there should be any overlap. But these particular 7 things, and here's a theorem that Nahm, it follows from the conjecture of Nahm and was proved, well, half proved by a student of Nahm, who showed that the only A values are these 3, and I completed and showed that the only triples are these 7. They're exactly 7 cases. So this modularity is very, very rare. It's very hard to have such a sum. So the intersection of the world of Q hypergeometric and of modular, so both of these are types of Q series, but the intersection is tiny, and in this particular class, if I take the Nahm sums, one-dimensional Nahm sums, there are only 7 cases, even though it's a triply infinite family, well, of rational numbers actually, 6-fold infinite family or something like that. So, and Nahm asked the question, can you identify why? And he discovered that in this case, you can associate to A the solution of Q, which is the solution of this equation, and then Q will automatically be in the block group. Why is that? Well, because if I take Q, then I have to check this condition x wedge 1 minus x, but Q wedge 1 minus Q is Q wedge Q to the A, by this equation. And Q to the A is A times Q, because it's the multiplicative group. And so this vanishes. And so this gives an element of the block group, but in general, remember we have this D, which goes into R. And actually this isn't quite right. D goes to R to the infinity, so to speak, because for every embedding of cube R into C, you can evaluate the dilogarithm. But if you're in a particular number field of degree R1 plus 2 R2, then the real embeddings, real numbers go to 0 under the dialog. And the complex numbers change sign under complex conjugations. So you've actually only, if I have an F, then this will only go to the R2. And then one knows that this is, this map uniquely identifies things in the sense that anything, if something is torsion here, if and only if its image under the dilogarithm is 0. So then Nahm made the wonderful conjecture that modularity, Nahm conjecture, that modularity of this Nahm sum implies that this associated class, so here it's psi A, in this case it's a sum of just one element, but in the multidimensional case it's more complicated. It will be a sum of as many elements as the dimension of the sum. Modularity implies that this class is torsion. That was a guess, and it's certainly not proof. And he also has a somewhat more complicated converse, not quite like this, but more or less if psi A for certain associated A's are torsion, then you can find B's and C's. So for instance, in the case of Q, the only 3 numbers in Q for which this psi A is torsion, you can show very easily on those 3 numbers, 2, 1.5. And they're exactly the 3 numbers for which you get modularity. So Nahm sums set up a connection, a deep connection. But the reason we look at Nahm sums is the Nahm conjecture sets up a very deep and very surprising and totally unproved conjecture between modularity and K theory, algebraic K theory. And I generalized that several years ago in a talk and then in conversations with many people to what I called a dream, but it's an exact sequence, but it's not exactly an exact sequence of groups because it's very vague. So it's an exact sequence of dreams, I like to call it. So here we have quantum topology, three-dimensional quantum topology, whatever that means. As I said, it's, when you dream, you're allowed to be a little vague. And this maps, it's an exact sequence of dreams. It maps to algebraic, well, to K3 of cube R, so to the block group, algebraic K theory. And the kernel is modular. In other words, what Nahm says is you start with the Nahm sum, and it has these, K characteristic numbers, A, B, and C, and you associate it with a number that happens here only to depend on A, which is this psi, and it's in the block group, and you ask whether it's modular, and then that's the abstraction. Only if this class in K theory, let's say contains, well, you don't have to condense with Q here, only if that class in K theory is trivial, you get modularity, and he says that more or less up to something, when it is trivial, you do get modularity. So I said, well, maybe the same thing is true at the level of GQTA2014 invariants and other common invariants, in particular something like the Kashaev invariant. So that's somehow the subject. So the Nahm sums motivated this, but there was no connection. But now we have actually many connections, which I may or may not get to mentioning. But at least now you know why they're in the title, what they are in these two versions of Q hypergeometric. So now let me become more, and actually start saying some things. So first of all, I won't actually use the original definition of the Kashaev invariant, but another one that I'm going to call J0, which is the, comes from the color-Jones polynomials, and the quality of these is theorem of the Murakami's. So I won't actually write down I won't write down the definition of either one, but if you have a note, it was certainly mentioned explained in detail and beautifully in Fuji's talk, maybe mentioned in some of the other talks. You have a sequence of polynomials called the colored-Jones polynomials. So J1 is somehow not interesting, but J2 is the usual Jones polynomial. So I don't want to write like that. I want to put the K upstairs, and the Q, it's a function of Q, and usually I'll drop the nut. So this will be again the function. It's now going to get the wrong polynomial in Q, so it's not quite a polynomial. It's called a polynomial, it's the wrong polynomial. And the coloring has to do with taking the corresponding finite dimensional representation, the nth one of SL2, but I don't care, for there's a recipe, which I'm not going to go into at all, that writes down this Jn of Q. And now, let me just give an example so you see what it looks like. If I take
What do you mean by J0?
sorry?
What do you mean by J0?
I'll explain. I'm in the process, but I need a little time. So here's a formula due to independently to Le and Zagier in this particular case. So you can see that this is a finite expression. Now there are comments to be made for that. The first is that if I want, I can cross this out and put infinity, because once m is bigger than n, then one of the terms in this product is j equals n, and then you have a zero factor, and so this is 0. So this is also a terminating, even if I write it as an infinite thing, this is a terminating Q hypergeometric series. And I prefer to write it that way, because sometimes I want to vary the q, and then I don't want to have to keep track of the n. So now if you look at this expression, you see that if q is a fixed root of unity, let's say it's zeta n, or any capital nth root of unity, then Jn for this fixed knot, or any knot, well, it's true for any knot, this thing as a function of n, Qn is fixed as a function of little n, is periodic. So it doesn't change when you change n by capital N. Here that's obvious, because that's why I didn't want this n, because I can go as far as I want. And now if I change n to n plus capital N, well, the only place where n appears here is in the expression Q to the n. But if Q is a capital N through unity, that only depends on n modulo capital N. So if you turn things around and don't think, let me look at J3, it's a polynomial. It's actually a very complicated polynomial. J1000 has roughly 1 million terms. The degree of this polynomial goes up like n squared. So it's very ugly to write them down. But if instead you think, let me fix the root of unity, and look at the values, then you get something very surprising. So let me give an example. Let me take the 300th root of unity, and I look at Jn for the 4-1 knot, and say to 300. Well, here it's positive. We'll come to the, no, sorry. I look at the absolute value of this, not positive yet. And now it turns out that this is less than 25 if n is 1 to up to 299. But it's approximately 5 times 10 to the 45 if n is 300. So the picture is this. You go from 0 to 300, and the values are all extremely small. And then one value is 10 to the 50, practically. And then it's periodic. Okay? So that's a very, very striking behavior. Now, since it's periodic, I can extrapolate backwards. And so I can now talk about J0. There isn't a zero-Jones polynomial, but I can talk about J0 of Q. If Q is any root of unity, it doesn't have to be the standard one, so it's a root of unity, then then it makes sense, because if Z is any root of unity, then Jn is periodic. And since it's periodic, I can extrapolate back. But of course, I can also say equals J capital N of Z if capital N is any non-trivial n, such that Z n is 1. It doesn't have to be the minimal power, but the same periodicity. So, and then it was proved, as I said, by the Murakamis, that the original Kashaev invariance definition I'm emitting is the same as this extrapolated backwards thing. But I don't want to think that it's extrapolated backwards. I want to think that it's J0. Because you'll see that whenever you have an explicit formula, the same is true for every other nut, there are always formulas like that. Now let's look at J0. Well, if I have J0, then Q to the 0 goes away. And Q to the n goes away, and this goes away. But then you see that this is just, so if Q, but remember this only makes sense if Q is in U infinity. The J0, you cannot, these are not polynomials. J0 is only defined on roots of unity of any order. So I know I've especially called them zeta, it's just Q, but we know that Q is that. And now I can write this as the sum. Now I can recall it, well, the n now instead of m. This first product, 1 minus q to the j, is exactly a Q-Klopfhammer symbol. But because q is a root of unity, q to the inverse, q inverse is the complex conjugate, so this is the absolute value squared. And that's why it's suddenly so big. In all the other cases, there's huge cancellation. But suddenly everything becomes positive, and this thing becomes exponentially big. And you see again, this is a terminating hypergeometric series, and it has this strange behavior. Now you have the Kashaev conjecture that tells you the volume. But actually there's much more. So now I come to the first thing where higher algebraic number theory is going to come in, or higher, more algebraic number theory. So as I said, the Kashaev invariant, the Kashaev conjecture tells you that if you take this, then it essentially looks like e to the cn up to smaller terms, where c is, well, it's the volume of M.
Sorry, Don, when you say it this way, I mean...
It's, let me finish the sentence before you correct me. Okay, I said essentially it looked like that, and it would be like that before one knot, but before I had an absolute value sign here. So the C before was the volume of the associated M, but actually you have to add the term Simon's invariant correctly normalized. So this is called the complexified volume, and then the conjecture now is like that without the absolute value signs, but actually much stronger.
But there is also something in front, right? I mean,
this is little O of n. There's nothing in front. And let me tell you, you'll see it's correct. Give me a second.
So a little O of n allows the power of n in front. Sure.
Log n is smaller than n if n is large, right? Mm-hmm. You agree? Log n is little O of n, so it allows in particular. Yeah, there's a little O of n. I'm going to be much more precise. In the second, our next result is due to Professor Anderson and his then student Hansen. So more precisely, so for the figure 8 knot, I already told you the volume is this, well, for the figure 8 knot, the volume is simply, it turns out, because of the triangulation, it's simply 2 times you take the 6th order of unity, which is 1 plus pi squared of 3 over 2, and you have true tetrahedron with that shape parameter, so the 1 over 2 pi is 1 over pi times this, which is about 0.323. And here there's nothing complex because everything is real, so the Kashaev invariant would tell you that roughly you get, in that case, e to this constant, 0.323 times n, but the more precise result due to Anderson and Hansen is, well, I don't know why I'm looking for this, I certainly know it by heart. There's an exact asymptotic formula proved in this case. In this case, the analysis is easy. It's the only case, that's the only knot, so far as I know, even today, where there's at least a published proof of the volume conjecture for a hyperbolic knot. It's this one. So here we not only know that the C is correct, but we have the full asymptotic, complete asymptotic equivalent. So these things are asymptotically equal. This symbol in mathematics has 2 meanings. One is that the ratio of the 2 sides goes to 1. That's all I mean here. But there's a more precise meaning, unfortunately, the same symbol, meaning a full asymptotic expansion. So I'll use this symbol, meaning the complete asymptotic expansion. And then there's a result which is due to Garifalidis and various collaborators. Well, it's unpublished, Costin and Geronimo, and also myself. So, and others, and myself. So he did it in 2 ways with the 2 collaborators. I did it in 2 ways, one numerical and not proved, and one rigorous. And the full result is that actually there's an asymptotic expansion. There's much, much more than just the original numbers. And so it begins 11 over 36 times the square root of 3 times pi over n, plus 697 over 7,776, which I hope everyone in this room can recognize. If you aren't, you should do topology and not number theory. And the next one is 724,351 over 4199040, which, to be honest, even I don't recognize anymore, although it's something very simple, and so on. So there's an entire asymptotic expansion. You start with the Anderson-Hansen result, and then it's multiplied by an entire power series, which is a power series, in this case, in pi over n squared of 3 with rational coefficients. And the rational coefficients are very, very complicated. They have denominators that are big but a very small power. This is a power of 6. And this is, well, it happens to be prime, I think, 697, so the numerators are whatever they are. So this observation was generalized. So this, as I say, is a theorem, but this is the only case where even the weak statement that you get this up to little O of n, the volume conjecture, this is the only note where it's known. So from now on, everything I say is conjectural if you actually wanted to apply to the Kashaev invariant, because we don't know even the leading term. But there's now the arithmetic conjecture, which was made independently by Garifalidis, whom we abbreviate and whom we don't abbreviate, because it's hard to make a 3-letter abbreviation of a 2-letter name. And the other is Dinofte, Bukov, Reynolds, I always forget. I put double F everything, I'm not sure. A paper of us on non-combat gauge group turn Simon's theory 4 years ago or so. And the conjecture says that in general, for any k, you'll always have that this thing, so this is the J0, or if you want the Kashaev invariant, Kn, this thing should always look like n to the 3/2 times, well, the way the physicists write it, which I'm not really enchanted by, but I'll do it anyway. They start at 0, it should somehow be -1, and then S1 and S times H. And on top of that, they put a bar in the H, but that I somehow refuse to do, because this is a number that has to be multiplied by 2 pi, and H that has to be divided still by 2 pi, and so it should be H, because in quantum theory, H bar is H over 2 pi, not H times 2 pi. So H here is going to be 2 pi over n. So you see that the leading coefficient S0 is conjecturally the volume, so that's our volume over 2 pi times n that I had. But now the volume the conjecture says that first of all you have not just this leading term and then little o of 1 over h, but you have a power of n. I think it's always 3/2, maybe it depends on the note. But then there's a complete asymptotic expansion, and the leading term, S1, is at the very least the log of an algebraic number, but actually it's a multiple, I think obviously, well, a certain multiple of a number in the trace field of the knot. So in the cases here, it would be, for instance, the log of a number in alpha. I'll write down the numbers here. So you saw that in the example that I unfortunately just somehow killed, there was an n to the 3/2, e to the cn, and the constant term was the 4th root of 3. So if I put it in the exponent, I get 1/4 log of 3, but up to roots of unity, that would be some log of, well, 1/2 times the square root of -3, and that, remember, was in our trace field. Well, of course, 3 is years and Q's, everything's in the field. So S1, after you exponentiate, it becomes an algebraic number, and now the really fun part is that all of the higher ones, so here the higher ones are these numbers, and you saw that if I do it, sorry, h should really be 2 pi I over n, because my zeta n was supposed to be q, and I always want to write this e to the h. Again, people tend to put e to the h bar, but it should be e to the h. So in our case, it's 2 pi I over n, so when you see this pi over n, well, up to a 2, I could put 72. This should be square root of -3, and you see it's then in our trace field. Because remember, for this particular knot, the trace field was 2 of square root of minus 3. And so the real interest of the conjecture is that all of these numbers are, so these are of course all not invariants, since the whole Kashaev invariants are not invariant, so is every term of the asymptotic expansion, if there is an asymptotic expansion, which is conjectural. But if it is, they're all not invariants. The first is the volume, which only depends on the class in K theory. And so when I made my dream, I made a dream conjecture that if two knots had the same image in K theory, in particular the same volume, the same image in K theory, then all of these invariants, not just the volume, but all of the invariants would be the same. And it took something like 4 years till Stavros and I could check this, because the first such pairs of knots, like the 5-2 knot and the 2-3 minus 7 pretzel knot, it's very, very difficult to compute the Jones invariant for large n's for the other one, and therefore to do the asymptotic. So we finally succeeded. And the conjecture was wrong. These did not have the same asymptotic expansion, only the leading term. But we now understand it better, and there's a part of the asymptotic expansion which now we know does only depend on K theory. And so at least some part was right. So let me give an example, a numerical example. I mean, all of this is, well, some things we can now prove, but not at the level of the Kashaev invariant, where even the volume conjecture, which is the leading term of this, is still unproved. So therefore the numerical examples become very important. So let me give example 2. In this case, this one. If I take the 5-2 knot, I've already told you that the field is Q of alpha, where alpha is that cubic irrationality. And so in this case, I won't write down the formula for the nth Jones polynomial just for the 0th one, so the Kashaev thing. But now I no longer need Q, remember, to be say to n. It doesn't have to be, it's just any root if any order. And so the formula in this case will be the sum n from 0, well, if q to the n is 1, it terminates. So again, I could put infinity or n minus 1. And then the formula is qn, the Hawkhammer symbol squared, times the sum k from 0 to n of q to the power n plus 1, I'm reading this right, divided by qk, bar. So this is already, that's a more typical expression. The other was a simple sum, this is a double sum. In general, you'll have multiple sums for both the J0 and the Kashaev invariant. Here, the dimension of the sum, in one case, it's the number of crossings of a knot diagram, in the other case, the number of tetrahedra, an ideal triangulation. Anyway, you get a multidimensional sum. Here, there's a trick. You can compute this in O of 1 steps from the previous one. And so if you do this, this can be computed in O of n steps, but it's a little theorem of Stavros and myself that for all knots, you need only O of n steps. And I'll say just very briefly why that is. If you look at the actual colored Jones polynomials, then it's a beautiful theorem of Garofalidis and Day, or Stavros and Tan, that they satisfy a recursion of finite length. This is related to the non-commutative A polynomial, which you mentioned. And therefore you would think, well, there's no problem, since when you go from 1 to n, if there's recursion, that's only n steps. But the problem is that the recursion at each step, you get 1 minus q to the n times jn as a combination of its predecessors. And that's why, see, the predecessors, remember in my example of 300, when I had 300 through infinity, the first 300 were very small numbers, they were less than 25. If I have a finite length recursion, just a few terms, how can it suddenly give this huge number? And the answer is it can't in the recursion, but because the previous, this is finite length recursion, there are 3 terms or something. So if those 3 are less than 25, how can this be 10 to the 50? But the answer is it can't, but this factor is 0. Because remember, the one I want is when n is equal to the order of q. So the recursion doesn't seem to work, and therefore this theorem is not entirely obvious, but the trick is very simple. If you have recursion for j, you can differentiate the recursion. You also get a recursion for jn prime, if you differentiate this. And now the 1 minus q to the n, sort of by L'Hopital's rule, goes away. So if from the beginning you keep track of j and jn prime, well, that's 2 things, but it's O of 2n, but still O of n. If you keep track of both of them, then at the end you get 2 numbers. One of them is 0, but the other isn't, and gives you your number. And then if you have a higher power, it still works. So but it's actually, I should mention this, it's O of n plus OK of 1. OK, O of 1 doesn't sound very bad compared to O of n. So in a typical case, if it's 4, 1, then the O of n was such a good constant, I could go easily on my computer to 50,000. Whereas if you just take Zagier or something and run it on Mathematica, then it'll give up on the Jones polynomials by the time n is 15. So you can't do any asymptotics with 15 numbers. You need tens of thousands. But if it were an O of n cubed, that could only go up to n is 200. So this was very important. But if I took the 237 Pretzel, then it took Stavros and a collaborator a year to work out between the time they started and finished to get the complete recursion. There's something like 200 terms. So the recursion is very complicated. So here the O of 1 is huge. It's several hundred terms and sort of a year of thinking about till they finally got the formula. So you have to do a lot of preliminary work for a given node to find the recursion. But once you've for a given node, you found the recursion, which is finite length, then you can program it and you can go up to 10,000 and 10,000 steps. But you have to do this big O of 1 first. So because we can go very far, you can test this. Well, I should mention, I was going to actually explain it, but I won't. There's a numerical extrapolation method that I found years ago, which is extremely convenient if you have a sequence of numbers that satisfies some asymptotics like the one we have, let's say an exponential times the power of n times the power series of 1 over n. Then there's a numerical method given, let's say, a few hundred of those to find the power of n, the exponential factor, and the first coefficient of the thing to very, very high precision. So, even though, let's say, n only goes up to 1,000, so since you have a correction term 1 over n, you'd think you'd only get 3 digits. But with this method, you can easily get 30 or 100 or 500 digits, depending how many terms you take. So you can compute by numerical extrapolation very well. In the case of the 5-1 node, where we have these very complicated coefficients, I wrote down the first few, then I actually found almost 30 of them that way, and by the end there's numbers with more than 50 digits in the numerator, and I found them all by numerical extrapolation. And then when I compared with Stavros' formula, which was more calculable than mine, then every single number agreed. So this numerical interpolation method can be used to find these expansion coefficients in all cases. Okay, now before I go on to modularity, which is actually my subject, I hope I'm still going to get to it, then let me say one connection now with the Nahm sum, which was completely mysterious, which we're now beginning to understand. So by sheer accident, Stavros now, 3 years ago or so, just an accidental discovery, he was looking at a completely different object. I won't even say what it was, but some other quantum object not associated to a node or even a 3-manifold. It's a so-called regular quantum spin network. So some quantum object, but not a knot, gave, in this case, an actual Nahm sum, which was this one. For convenience, I'll put the infinite Blockhammer symbol in front, but that's just a factor. It was this, it's not exactly like the original Nahm sum. This is just like Nahm, but there's a sign, and also in Nahm sum you have Qn, and here it's Q. It's sort of slightly generalized Nahm sum. He needed this particular thing, also coming from quantum invariants, but now a different kind of quantum invariant. So quantum something, quantum spin networks. And so he said, you're good at asymptotics, and we've done a lot of asymptotics together. Can we please do this one, even though it's, it has nothing to do with our business on notes, but we'll do it. So we expanded this thing. This now actually converts in the unit disk. So now it's quite different. Before we'd simply defined only at roots of unity. This makes no sense at roots of unity because the denominator becomes infinite, but it makes sense for q less than 1. And so you can take the radial limit as q goes to 1 or to -1 or to I or to some root of unity. And so we first did that one. It's very, very tricky because there are different oscillatory terms that are cancelling, but we finally managed to do it. And then we got several terms of the asymptotics, and then we each recognized something. There was a real number, and he recognized numerically the value of the volume, the renormalized volume of the 4-1 knot. And then there were some rational numbers, and one of them was 697. I said, wait a second, I've seen 697 somewhere. And so I went into our directory, typed grep 697, and found it was this number. And so we found that the asymptotics of this Nahm sum, which has nothing to do a priori with topology, at q tends to a root of unity, any root of unity, so it doesn't have to be the standard q, correspond in a very specific way exactly to all orders. We did many terms and the whole power series expansion to the asymptotics well, first let's say q goes to 1 because I haven't told you about the others. So q goes to 1, you got this entire expansion to all orders of the Kashaev invariant for 4-1. So there was this completely mysterious relationship, and so that not only are these things analogous, as we already knew, but but actually related, and we still don't have a complete proof of that.
Just the service information, it's now 9:50.
And I started at 9:30?
No.
It was worth a try. Sometimes he's thinking about something else, you know. Okay, that was an excellent service because he helped you a lot, because now I'm going to stop talking so slowly so you don't have to be bored and go to a normal tempo. So thank you for that helpful remark. So modularity. So let me stick to the 4-1. So at one point I said, well, you know, why the topologists always look, and the physicists always take Q as e to the h, and so h you sort of think of as very small, so Q is always tending to 1. And I said, well, let's look at another invariant. So I took this J0 invariant for the, then I took it now at minus A to n. After all, why not? It's now tending to a different root field, in this case minus 1. So what I first found was no surprise at all. I'll write it. It's the fourth root of 3. I've erased it, but in the Anderson, it's still there. The Anderson form that this was in the denominator. Now this is denominator 2 to the 3 halves, the same n to the 3 halves, the same Cn, except it's divided by 4, and then a very similar expansion to the one I won't write down the next coefficient. It is the same denominator, actually. It's 7776. All the denominators are the same. It's very, very similar to this. And so if you're me, and you see this, you would just yawn. So what? It's not that surprising. So it's a new expansion. The interesting part for the volume conjecture, well, it's the same volume. You don't get any new volume. It's just divided by 4. And if you do it at a cube root of unity, so by putting the cube, then you'll get, you know, Cn over 9. So it looks very boring. But this is not true. This is true if n is congruent to 2 mod 4. But it's asymptotic if n is 0 mod 4. Then the leading term is 5 times what it is. But now comes the amazing thing. You do it using my extrapolation method. I did 20 coefficients of this thing to very, very high accuracy, identified all of the numbers. When you do it for n 0 mod 4, you get exactly the same expansion. Every single number is the same, the 41, all of them. There's only 5 in front. And if n is odd, then you get 27 times the same expansion. So now there's something very interesting. You have 1, 5, and 27. Well, it becomes more interesting if I give you a little table. Let me actually change by drop to j of x, where x is a rational number, would be j0 of e to the 2 pi I x, relative to e of x. Okay? So it's easier to work, and better, for my purpose, to work with the rational number. So let me give you a little table for the 4-1 knot, x and j for the 4-1 knot of x. When it's periodic, and also because this is an antichiral knot, you can reflect x. So the first rational numbers are 0, a half, a third, a quarter, the fifth, the sixth. Well, no, the fifth and 2/5, because it's up to reflection, but the fifth and 2/5 are different. 3/5 and 4/5 are then the same. And the values, well, actually, I think I know them by heart. It's 1, 5, 13, 27, 46 plus 2, I think that's the square root of 5. Maybe it's some other number, 22, I forget. This is the complex conjugate for 6, it's 89. So you get some numbers, but notice 1, 5, and 27. So this factor, to make it correct always, you have to put the factor that depends only on n mod 4. Remember, this j function is periodic at period 1, because it only depends on e to the 2 pi x. So the amazing thing was not that you had a similar expansion, and again with the full arithmetic conjecture, that you have these strange numbers, but that there's a factor in front, but there's another value of j. So what we have here is that j of minus of 1 over n in this case, sorry, of a half, plus 1 over n, is equal to this times a nice power series. Okay? So, well, but now you notice that these things are simply, you send x, I think x over 2x minus 1, which is on, well, SL2z here. If I put a minus sign somewhere, it would be minus, then it's in SL2z. This is a modular transformation. And so that's something that I sort of made this modularity conjecture. If you look at the expansions around rational numbers, then you will always get a beautiful power series with the same mysterious properties. I'll write down an example in a second. But it's multiplied by a factor, which takes on only finitely many values. Here, 1, 5, and 27. And that's j at this transform point. But actually, it's not, because now, once you know this, you could say, well, now why does n have to be an integer? So if you try this when n is, let's say, so here n might be 10,000, and this would be true, that would be the factor. But you can also take 10,000 and 2/5. But then this will be still a rational number, and so is that, and it still works. And now you can actually go back to the original j, and remember that the original j of 1 over n was equal to, you need to see n of n to the 3 halves times the fourth root of, n to the 3 halves, fourth root of 3, and 1 plus dot dot dot. Then this is still true if n has the form a large integer plus 2/5. Except that now there's a constant in front, and the constant is just the one that I couldn't remember by heart. I'll write it. You have to multiply, well, to say you have to multiply by j, by j of 2/5. So the modularity conjecture, so now it's engendered by n. See, before we didn't see it because n was an integer, and this thing has period 1, and j of 0 is just 1. But in fact, this works just as well if you do the modularity. Take the Kashaev, so this is not a Kashaev invariant because that was only allowed to be 1 over n. But this means I'm taking e of, let's say n is n plus a fifth. Then I'm actually taking this, which is no longer a pure reciprocal, but it's still going to 0. And now I find that I get exactly the same asymptotics as a function of n plus a fifth, but up to a factor, and that factor would be this 46 plus 22 squared root of 5, whatever j of 2/5 was. So the modularity says something non-trivial even there. And there's a very visual way of looking at it, which I wrote, I have a paper on that called Quantum Modular Forms. If you make a graph of the Kashaev invariant itself, or here it's log, you get something that's kind of dense in the plane. It's a horrible thing. But if you look at the graph of j of x minus j of minus 1 over x, well here it's even, so you drop the x, then suddenly you get a curve. Now you probably can't see that, so we've made handouts, and this can go through, and you can all take a copy home and enjoy it. It's on the back, yeah, so there's just one page per person. Okay, so there was this kind of amazing modularity conjecture, and now the modularity conjecture gives you new numbers. And I'm very close now to the end. So let me give you now a numerical example. So the full conjecture would say that, for instance, if I take, so let's take this element of the modular group, 5, 1. That's the example I just took. So now I would look at this j function for the 4, 1 dot of m over 5m plus 1. Well, now, as I said, I'll get an expansion like before, but it's much more complicated. So again, there'll be there'll be a power, well, pi over h to the 3 halves, where pi is again what it was before, 2 pi I over n, and there's an exponential function, well, you have a sum, s0 of, in this case, a fifth, s I of the fifth times h to the I minus 1. So again, there's a conjecture that you have an asymptotic expansion of the same general form as before with numbers, but now the numbers are much, much harder numbers. So let me give an example just for a fifth. So now, before we had these si, and that was the expansion that you saw here, but if I took the log, 1 over 36 square root of 3, and so on. But they were all in the ground field here, which was square root of minus 3, so in the trace field. But now they're not. So for instance, if I do it at 5, then the factor that you get in front here, the S1, turns out to 3 parts. There's a part with denominator, it's a log. One part is denominator 2, one part is denominator 10. You combine the two and make it 5. So this was all found by the numerical extrapolation procedure, purely numerical, where epsilon 1 up to epsilon 3 are units, and pi 29 is the prime of norm 29 in the field Q of zeta 15. But the way you should think of that is we start with the original field. It happens that it's cyclotomic, but that's an accident. That's because our F here was cyclotomic. The field Q square root minus 3, which is the trace field in this case, is also the field of Q groups of unity. So what this really is the ground field, the trace field, and you join the fifth root of unity, and in general you have to join the root of unity at the place you're looking at. Here we're looking near a fifth. So you have to join e to the 2 pi I over 5. And so that's S1, and S2, just to give you a feeling, remember in the previous conjecture, S1 was supposed to be a rational multiple of the log of something in the ground field. And the ground field before was the trace field F. Now it's the trace field that joins zeta 5. And just to give you a feeling of the numerical field, it's very, very hard to find these numbers. They're easy to verify, but there's no way to find them. Well, there is a way, but you need hundreds of digits and a lot of numerical work. So again, with the same units.
So John is now 10, just another surface information.
Oh, excellent. Now I will go into negative speed. Okay, so I will stop extremely fast, but I mean, this is somehow the point of the thing that now very deep number theory comes. Suddenly now, for every knot, and this zeta, if I take this j, which is j0 equal to by x, as x tends to some rational number, let's say with the denominator n, then you get an entire asymptotic expansion where there's a factor in front, which is the modularity, which the handout explains to you. But after you've removed that factor, you get a fixed power series, and that power series is always the same. There's a volume term, which is easy to predict, but the remaining terms, the first one is a very complicated log, and the next one is some incredibly complicated number, and then there's this very mysterious pi 29 that you get the square of in the next term. But what's the deep meaning of pi 29? Why is there a pi 29 here in the log? Here, well, that turned out just because the topologists have brainwashed us, and the physicists with quantum group theory. You shouldn't take it as the sum, after I take out the exponential factor, you shouldn't take the sum S1 plus S2 h squared and so on. You should write this instead as an ordinary power series. And if you do this, then the pi 29, well, the leading term is the same, so this pi 29 will be in front, but then the next term is whatever it is times h. There's no pi 29 ever again. It's just that when you insist on taking the log, then you write this as pi 29 times now 1 plus something with the 29 the denominator. So these 29s that we thought for 3 years were the deepest invariant, we had no idea. It's just an accident. So now just to end in the remaining time, in the last few weeks, we have proved completely the modularity conjecture, which was a complete conjecture for the 4-1 knot. You can't expect it for any other knot, since even the leading term isn't known. And we have an algorithm that associates generalizing some work of Tudor and Stavros, the Dimorph and Garfalidis, not on first name terms, with a way that assigns to every such alpha, it assigns specifically this power series. So I don't want to write with the SI, but I want to write as a power series. So this power series, you can give an explicit power series, which is well defined, which, well, for their invariant, no, for their invariant, it's not yet known to be a not invariant, but it's a power series in H that we can predict. And so now we did it for the 5-2 knot and the 4-1 knot. We compared with all the things. It predicts the 5 pi 29. The formula gives the pi 29, and it gives this unit, and it gives this. The const term always is like that. There's a term, well, after exponentiate, a square root of something, an nth root of something, and then a number in the ground field, well, the whole power series. This is a prefactor, and this is always the nth root of the unit, and this is always the square root of something which is ramified, only involves ramified primes. For these two, it will only involve primes above 3 and primes above 23. So the part where you take an nth root is always a unit, and then there's a part which is in the ground field, and the unit, through some joint work with Caligari and myself, one also can make a guess from the true algebraic K theory, as opposed to the block group, of what it is. Our thing is defined by the block group. So we now have a proof of the modularity conjecture in the one case where there was a chance to prove it, and a recipe to give, so the conjecture, which before was that there exist some algebraic numbers with all of this, we can now say the following algebraic numbers are first of all well defined. We don't know that they're not invariant. We change the diagram and they give the right answer, and all this works, and these are sort of 50-digit calculations, so it's certainly true. Okay, I'll stop.
Questions?
Yes. I have a single question. Do Nahm sums satisfy any? So can you find any Q-difference operator which annihilate them?
Well, that doesn't quite make sense. It's just one object. A Q-difference operator, you need to have a sequence of things to make. So no. But of course, they're Q hypergeometric, so the individual terms, of course, satisfy Q-difference relations. And that's how you can analyze them. That's what it means to be Q hypergeometric. But the sum is just one object. So, there's nothing like But there's nothing like a Q differential equation or anything. But you wouldn't expect it. After all, modular forms don't satisfy any reasonable, but they do satisfy some kind of nonlinear differential equation. But basically, no, that's not what you somehow would feel should be right.
You also mentioned that you think there's some part that's determined by the element in the block group.
Yeah, yeah, that's right. Thank you very much for that kind question. So I mentioned here that after we do this, in all the experiments, so I just gave you an example. After I've exponentiated, let me exponentiate these things, you can see it better. So here the power series associated to the 4-1 group around the point of fifth or 2/5 was first the exponential of this. So it has a term which is the square root of 5 cubed over 3. Then it's the, well, and times some unit. If I split the 10 into 5 and 2, then it's the fifth root of a certain unit that happens, you might know, I didn't explain what it is, but some simple units, and then it was times, and then it was A0 plus A1, and so on, where every A is in the ground field, which you see of the trace field that joins M. But here, these numbers are not in the ground field, you need a square root and an mth root. And so here, in general, you'll get the mth root of the unit, and epsilon is supposed to be in the unit group of Fm, which is this F adjoined mth root of unity, but, of course, it's only defined up to mth powers of units. Because you could change this by an mth power and then put that extra unit in all the a's. And so this is the part that turns out to be k-theoretical invariant, and that's the work with Caligari and also ours. We do it with the block group, he with k-theory, well, it's done with me, but he actually did everything, all of the thinking, asked the questions. It turns out that there is, if you look at this group, this epsilon has a very surprising property. Namely, you know the Galois group of Fn over F. It's generated by the sigma A, which sends Z to A. And this unit has the extraordinary property that if you take the 8th conjugate of epsilon, it's the 8th root of epsilon. Notice its 8th power is epsilon times some other unit, the nth power. And you showed that if you take the subgroup of this with that power, its rank is exactly R2. And there is a map from K-theory to that. And we didn't show its rank, well, the rank part is easy. We didn't give a map from K-theory, we gave a map from the block group. It's not sure that they're the same because his is abstractly defined. So this is the part, the mysterious thing that you have to take the fifth root, that invariant, the part that isn't the nice part. So this part is sort of random with the pi 29 and so on. That's the part that depends on the individual knot. But this prefactor, and also the discriminant basically, but this prefactor is the K-theory invariant. So thank you very much. That's the part that only sees the class in K-theory.
So, any more questions? Let's.
You hear you're not allowed to.